In this AP Statistics video, we're going to briefly review and, or, and independence relative to probability, and then I'm going to introduce conditional probability in the second half. So for our first problem, we're going to look at the event where we toss a coin and roll a fair six-sided die. What is the probability of flipping heads and rolling a 4? And I want you to pay special attention here to the notation. PH looks like an upside down capital U 4. So that's the math symbol for and. You probably got that from class. So what I'm looking for is flipping heads and rolling a 4. And when we look at the overall sample space, we notice that there are 12 possibilities, and only one of them is flipping heads and rolling a 4, so 1 out of 12. Now, for the probability of flipping heads or rolling a 4, and again, catch the math notation of this, or remember has a different mathematical notation than it does common English language usage of or in English language, remember, tends to force you to choose one thing or another, but not both. In mathematics, it is quite okay to be doing both. So if you happen to be flipping heads and rolling the 4 at the same time, that's a perfectly acceptable for or. So remember, in English language usage, it is an exclusive or. In mathematics, it's always an inclusive or. So to flip heads, let's satisfy the first piece of this. Flipping heads, there were 6 outcomes altogether. Rolling a 4, there were 2 outcomes for that. But notice this first piece that we had used in the first probability is actually a legitimate use in the or. It is possible to both be flipping heads and rolling a 4 when you're working with an or situation. So what I can see in counting, there are a total of 1, 2, 3, 4, 5, 6, and 1 additional. So altogether, there were 7 in the or out of the 12 possibilities. So next, what about the probability of flipping heads? And that symbol is a given. So what we're really looking at now is a conditional probability. And conditional probability says if I want to know the probability of flipping heads, but what I'm given, the condition is I just rolled a 4. Given that I just rolled a 4, what is the probability that I flip heads? So coming back up here to our sample space, what I was given is that I just rolled a 4, so I'm looking only at those possibilities. And of those, what is the probability that I flip heads, which is this guy? So that probability was 1 out of the 2 possibilities that existed when I was rolling a 4. All right. And that seems like it was had a pretty easy way of understanding that. So let's talk again about independence. You should have had that from your last class. What happens if you've got a situation of probability of some event A given some other event? And this is a formal definition of independence. If A is independent of B, then the probability of A isn't bothered by the existence or non-existence of B. So that is simply P of A. Probability of A given B is just the same old probability of A as it always was. A is independent of B. It doesn't matter what B was. So when we go back to that last probability we had computed, what's the probability of flipping heads and rolling a 4? Well, rolling a die has no effect on the coin. So that is really just the probability of flipping heads. And from a regular coin, you know the probability of flipping heads is just 1 out of 2, which is the same result that we got up above. So when, because independent, when you have independence, a conditional probability actually turns out to be a lot easier. You just ignore whatever the condition was because it had no effect at all on the probability in the first place. All right. So, what about the probability of computing a typical AND statement? Remember, the upside down capital U means AND, probability of A and B. So in general, to find the probability of A and B, what has to be true is that both of those events have to happen. So I need to know the probability of A, the first one. And you learned in class that once you have the two separate probabilities, you're multiplying together. So I now need to know the probability of B, but there's a special condition here. I don't really know if B is, in general, I don't know if the probability of B is affected by the probability of A. So when I compute the second one, I have to do probability of B given that I already have A. A already happens, as indicated by the first part of my equation. But we just learned that through independence, if those two events happen to be independent, then this conditional probability is really just P of B, but that is true only if B is independent of A. All right, you have to have that in order to change. So basically, I'm not recommending really lots of formula memorization here. I think that's sort of the wrong way to go about this. But think about what it means to compute individual probabilities. So the probability of A and B means both A and B have to happen. So the straightforward approach on that is probability of A, that has to happen, and then multiply by the probability of B given A. And if B happens to be independent, I've just got a simpler version of this. And that's really what we're going to be playing with. So down here, computing our next example, probability of flipping heads and rolling a 5. Well, flipping a coin and rolling a die are completely independent events. So this is the same thing as probability of getting heads times probability of rolling a 5. And the probability of heads was 1/2. The probability of rolling 5 on a fair die is 1/6. Altogether, that's 1/12, which if you look back at our earlier example, it was with rolling a 4 instead. But that's exactly why this thing was 1/12, and I could have computed that without looking at the table. So next, computing P given A. So we're still given or under the condition of A. We're still looking at conditional probabilities. As an intuitive understanding of sample spaces, really, if I were to look at this particular example to try to show us probability that the sum of two dice is greater than or equal to 10, given that the first thing you roll is a 5. So what I could do is look at the entire sample space of rolling two dice. And there you have in black on the row and column headers the outcomes of the two individual dice, and shown in red are the rolling possibilities, the sums of those dice. So what is the probability that the sum is greater than or equal to 10 given that the first die is a 5? Well, perhaps the easiest way to do this is to say, well, look, I was given that the first die was a 5. So let's just look at the part of the sample space where the first die was a 5. And of those, which one has a sum greater than or equal to 10? That would be those two events. So that probability is just 2 out of the 6 given events represented by the first die being a 5. So that probability is 1/3. All right. You can also, some people prefer to work through formulas. Personally, I think the intuitive understanding of a conditional probability just restricts the sample space. That's a fundamental idea for me. A conditional probability restricts a sample space. But some of you like formulas, so let's go that way. If you remember earlier, the probability of A and B is the probability of A times the probability of B given A. Well, notice I've got a conditional probability, and this is just an algebraic equation now. So I could solve for that. The probability of B given A is just the probability of A and B divided by the probability of A. So I now have a formula that I can solve for. So over here, probability of B given A, so this must be event B, this must be event A, probability that the sum was greater than or equal to 10, given that the first die was a 5. So that is going to be equal to, by what we just had, the probability that the sum is greater than or equal to 10, and the first die was a 5, divided by the probability of the A, which is the probability that the first die was a 5. So if I go back and look at these, now what's important to remember that these two probabilities are both referring to the entire sample space. So when you look at this, when you try to compute conditional probabilities using the intuitive understanding, what you do is you restrict the sample space. If you want to think of them through formulas, then what you're going to be doing is looking at the entire sample space at once. So I needed to compute the probability of the sum being greater or equal to 10 and the first die being a 5. So in the entire sample space that I have, that happens here and here. So that is the intersections of the sums being greater than or equal to 10 and the first die being a 5. So that was 2 out of my 36 possibilities. Now, what's the probability that the first die was a 5? Well, for that one, there are 1, 2, 3, 4, 5, 6 out of the entire sample space of 36. So that tells me there are 6 out of 36, which simplifies down to 2 out of 6. The exact same answer that I got before, but now I figured it out through a formulaic approach. Some people prefer the formulas. I personally prefer the intuitive understanding of sample spaces. It's up to you. They both give you the same answer. All right, for a slightly different kind of problem, another example for us. Let's look again at that table that gives the male and female representation in the current U.S. Senate as of August 2015. And the question is the likelihood of a randomly chosen U.S. Senator being female independent of party affiliation? So remember, by definition of independence, let's do F for female and P for party. So what I need to know is the probability of being female given party affiliation the same as just the probability of being female? If that is true, then being female in the U.S. Senate is completely independent of which party you are in. So can we solve that as an intuitive understanding of sample spaces? Well, what is the probability of being female? And actually, folks, this is a pretty important piece here. If you are ever asked whether or not two events are independent, you actually need to go through and show this particular process. Is the probability of the first one given whatever equal to the probability of the event not without the given? So what is in general the probability of being female? Well, there are 20 female U.S. senators at present out of the total of 100, so that is 20 out of 100. And what is the probability of being female given a party affiliation? So let's assume here for a moment that P means Republican. Well, here are the Republicans. What is the probability? So thinking of it as an intuitive restriction of the sample space, I had my entire U.S. Senate, but now I'm just given Republicans, so I'm just going to focus on the bottom row. What is the probability of being female? Well, that is 6 out of the current 54 Republican senators, and those two are not equal. That's all you need to prove that no, the probability of being a U.S. senator being female is not a randomly chosen U.S. senator being female is not independent of party affiliation. Now, just in case you think I'm picking on one party over another, what if P meant independent? Well, I know the probability of being female is 20 out of 100. In general, that satisfies the first piece. What is the probability of being female given that particular party? So, not party, independence. Well, as an intuitive restriction on the sample space, I'm now dealing with the middle row. So the probability of being female given that I am independent, well, that's 0 out of those two possibilities. This clearly is not equal. Again, you don't need to show both of them. You just need to show one. Knowing the party affiliation clearly restricts or changes the probability of being female in the U.S. Senate at present. Could I solve this with formulas? Well, of course I can. So the probability of being female given, I'll just go back and use the Republican example, is that equal to, well, what I need to figure out is this guy should be the probability of being female and Republican divided by the given probability of being a Republican. And remember, since I'm using formulas, I'm now looking at the entire sample space. What is the probability of being female and Republican? Well, there are 6 of those out of the entire U.S. Senate, so that's 6 out of 100. What is the probability of being Republican? Well, there are currently 54 Republicans out of the entire Senate, so 54 out of 100, which, if you eliminate the common denominators in both the top and the bottom of the probability fraction, that reduces down to 6 out of 54, which is exactly the response that we got when we were looking at it as a restricted sample space. So why do these two approaches give exactly the same result? In general, what happens is, remember, when you're using the formulas, you're thinking in terms of the entire sample space. So both of them, both the numerator and denominator, are going to be essentially, or could be written with the same overall sample size denominators, which cancel out. So what you're going to be left with really is just that probability from the restricted sample space. I think that's another reason why, at least for me, it tends to be easier to think of conditional probabilities as just restricted sample spaces. So hopefully this helps, and good luck with your homework.